What are we talking about today? Systems of equations. Haven't we already done that? No, so some has to be different, right, for us to start. Okay, but let's think back to what we do know. Okay, when we had a system of equations, how many possible solutions did we have? Couldn't I get one solution? And what did one solution look like? And where was the solution? At the point of intersection, right? The point of intersection was the solution. So we had an option of one solution. What else did we have an option of? No solution? What did no solution look like? Parallel lines? Okay. So one like right there and one like right there. Right? That was no solution, correct? What was our other option? If you have two lines, can you have two solutions? Can you draw two lines in such a way that you get two solutions? No, right? Okay, so think about something else. What was our other possibility?
Undefined.
Here was our first line. Here was our second line. How many solutions is that? Infinitely many solutions. So if we've already done systems of equations, why are we doing it again? Well, because something's different, right? Something's different. So what about this? What have we been talking about lately? Quadratics. So what if I had a parabola and a line? How many solutions can I get? Two, right? I have two solutions right here, correct? Where they intersect are the solutions. Is that the only possibility, is two solutions? What else could I have? One? What would one solution look like? So like a vertical line? Because any sort of other diagonal line is going to be two solutions, is it?
Yes.
Or is it?
No.
What if I had my parabola right here, and then I had a line right there? What kind of line is that? Remember what it's called? I want you to think back to geometry. Oh, a tangent line? By definition, a tangent line is a line that touches something in how many places? One, right? So is it only possible that we get one or two? Or could we get none? What would no solutions look like?
Lines not touching at all.
So how would that work? Like the parabola is right here, and the line is where? Like this? Or horizontal, yeah, for sure, right? That would be no solutions. Could I get infinitely many solutions with a parabola and a line? No, why not? They have to lie on top of each other, right? Now I can't do that with the parabola and the line, right? But what if I had two parabolas? How many possible solutions could I have then? Okay, what would that look like? Here's my first parabola. What would my second parabola look like? So you want it to be on top of it like this? You're fine. How many solutions is that? Infinitely. Infinitely many, right? What's another possibility?
Do it the same or like opposite, like mirror, like that.
So how many times are they touching? Twice? Okay, so you're saying we have one here and then one like here? So 2 solutions? Can I have one solution? What would that look like? Here's a parabola. The other parabola would kind of have to either be here What's another possibility? It's okay, it's okay. What's another possibility?
If it's like
So if it's like this, right? If the vertexes are touching, like that. Are there any other possibilities if we have, let's see, so far we have infinitely many, we have 2, we have 1. Is there any other possibilities if besides infinitely many 1 and 2? What about none? What about no solution? What would that look like? So how would they not touch at all?
Kind of do like what you did on the one solution right before it, and then just space.
Oh, right here? So one there,
And then one just down below.
one down there where they don't touch. Okay. So infinitely many, none, 1, and 2. Is that the only options?
I bet there's more. Hold on. There's gotta be like 4 more. Those. Probably.
What about 3?
Yeah, probably. Like 4.
Could we have 3 solutions? Say it again.
The line was going through it, right?
So if we had a line and a parabola, could I have 3 solutions?
Like a line and two parabola.
So you want 3 graphs? Right now we're only dealing with 2, because we have a whole nother, it's a whole nother can of worms, right? If we start adding another graph onto here. Right now we're just talking about having 2 different things, right? If I have 2 parabolas, can I get 3 solutions?
I can't think of how that would work.
Do you mind if I show you?
No, you can show me.
I can, okay. One, 2, 3. Why didn't we think about those? Why didn't we think about sideways parabolas?
Because we don't do a lot.
We don't do them a lot, right? We're usually focused on functional parabolas, parabolas that only open up or down. But have we talked about parabolas that open sideways? Yeah, so we know they're a thing, right? So this is 3 solutions. Is 4 possible? What would that look like? So 1 up. So it's still opening left or right, and you're just saying I needed to go further this way so it can come back this way. So 1, 2, 3, 4. Are there 5? Could there be 5 solutions?
could be 5.
How?
Hang on, give me a second.
No, I appreciate the fact that you're thinking about this. That's good.
If you go 1, 2, this way, 3, 4, obviously we can because she drew a graph, but she don't have to show us how. Right? No?
Is that right?
I don't know of a way you can do 5.
Oh, so,
I was just trying to trick you, I guess, by drawing a graph. I do have another graph to talk about, but I don't know of a way that there's 5. I don't think you can do 5.
can I finish that?
If there's a way, I don't know it, which, to be fair, there's a lot of stuff I don't know. Right? I don't know how to fix an engine. I don't know how to do brain surgery.
Unless you could draw 1, 2, and 3, but you can't draw 3.
You could think about it later, right? Okay? Is there another way to get 4 solutions?
Yeah.
Yeah, you get 4 solutions. You just did 4 solutions.
Oh, no. Oh.
Pretend that's a circle. It's a terrible circle. It's terrible. But you're pretending,
Better
right?
than what I could do.
1, 2, 3, 4. Isn't that 4 solutions? So why didn't we even think about a circle? Yeah, we haven't done circles, right? Circles are geometry, aren't they? But we can still have the equation of a circle in our system, can't we? So if we have a circle, can we have 3 solutions?
Yeah, you can. You could just wait. Hold on.
Yeah.
If you go over the thing, or like,
Pretend this is really a circle again. 1, 2, 3. So if I have a circle involved, can I have 2 solutions? How? Oh, I'm so terrible at drawing circles. Like that?
I didn't catch up.
that's it.
Another way to get 2 solutions? Okay, that one's a little bit better. What about that? Isn't that 2 solutions?
Yes.
If we have a circle and or a parabola and or a line, is there any way to get infinitely many solutions?
No.
No? What would have to be true about the 2 equations that I have for me to get infinitely many?
Deal. I don't know.
The only time we got infinitely many are these 2 right here, right? So what's true about both things that I graphed?
There were this.
They're the same kind, right? These are both lines, these are both parabolas. So I could get infinitely many solutions with a circle as long as the other one was a circle, right? What about no solutions? Could I get no? Well, I'll go ahead and draw. Let me draw infinitely many. Could I get no solution?
Yes.
With a circle?
2 circles that don't touch.
2 circles that don't touch?
Right.
Could I get a no solution with a circle and a parabola?
Yep.
How?
1 circle up there, and then 1 way down there.
So like the parabola is down here?
Yeah, like way over down there.
Or like a circle and a line, if the line was way down here? That would be possible also, right? So that would be no solutions? So, do you have an idea of what these could look like if I graphed them now? You have idea? First of all, did we graph all of the possibilities?
No.
No, it would literally take us infinity to graph all the possibilities, right? I don't really have that much time. I have an appointment this afternoon. So but we have a good representation of the possibilities, don't we? Okay, so I need us to think back for just a second. When we solved systems of equations, before when we did it before, what were the ways that we knew how to solve a system of equations?
One solution?
Oh, that's the types, so that's good thinking, but what were the ways that we solved them? Graphing was one way, which for the record we kind of just took care of. We're not going to take the time to actually solve them by graphing, because what could we do if I gave you two equations? What could you do with those two equations? Put them in your calculator, right? Okay, so we're not going to take the time to do that. What's another way you knew how to solve a system of equations? Substitution. Matrix. And elimination. Good. Okay, so graphing, we just did it, right? So it's done. And matrix,
Calculator. That's easy.
except we can't. Guys, the only time you can solve a system of equations with a matrix is if you have lines. Only lines.
X.
Okay? The only one of these examples that we did were lines, were the ones in the beginning to remind you what we were talking about. Since we have parabolas or even circles as our possibilities, we can't do elimination this time. Or excuse me, we can't do a matrix this time. Okay? So what I would like to do is take you through some examples of substitution and elimination. These are the two ways that we're going to solve a system of equations this time. Okay? You got that okay? Let's do this one first. I had it written down before you guys came in here. I didn't write it down that fast. I just moved a piece of paper that was on top of it. You couldn't see it. So these directions, you know how sometimes they tell you exactly how to solve it and sometimes they just say solve? These directions say solve with substitution. Okay? Solve with substitution. Now, if you see this equation right here, I hope that it doesn't have to tell you to solve with substitution. I hope that's the very first thing you should try, or that you would try, because of the fact that they both already equal what? Y. If they both equal y, isn't it easy, just easy enough to take this part and put it right there?
Oh, right.
Right? So if we do that, we get negative 3x minus 17 equals negative 3x squared minus 30x minus 71. So how should I solve this from here?
And you gotta, you would subtract 17 from 71.
Why do you want to do that?
Because it's the first thing I thought of.
And it's the first thing you thought of because you're trying to get it equal to 0, right? So if we subtract 7 or add 17 to both sides, what else should we probably do? Yeah, absolutely. Add 3x to both sides. Okay, now you don't have to do this, but notice that I put it under the like terms that I want to combine it with, right? So 0 equals negative 3x squared minus,
27x.
very good, minus
Like 54.
exactly 54, right? Negative 54, but it was already there. So now if it's 0 equals this, what am I trying to do? I'm trying to solve it, right? I'm trying to solve this for x. So, well, what do I do? How do you want to solve this for x? What are all the ways that you know how to solve this quadratic?
Graphing square roots, factoring, completing the square, and quadratic formula.
Yes.
Which is
Which way do you want to choose?
quadratic formula, so we can sing.
Oh, so you want to choose quadratic formula just so we can sing?
Yeah,
I'm fine
make
with
sure
that.
Everybody knows it.
Okay,
Make sure it's
so
on it.
but before we sing, we need to identify our variables, right?
Hey,
A,
Sean, do you know it?
B, and C, right? x equals negative b plus or minus the square root of b squared minus 4ac all over 2a.
Why do you sing it so slow?
Because I was trying to write it.
Oh, that.
Yeah, that's.
One more time for Sean to wait.
Yeah, I think one more time sounds good.
So you all have your calculators out, right? So we can work on this? Oh no? Okay, I'm not going to be the calculator slave today. We're all going to work on this. Right? X equals 27 plus or minus the square root of negative 27 squared minus 4 times negative 3 times negative 54. Notice what I did with the negative 27? Before I squared it, what did I do? I put it in parentheses, right? If I'm going to square a negative number like that, I need to make sure it's in parentheses, otherwise it's going to give me the wrong answer. Okay? Equals what? 81 over negative 6. Now, this is really good, right? Why is it really good? We know the square root of 81, don't we? X equals 27 plus or minus 9 divided by negative 6. What's 27 plus 9?
27 plus 9.
Correct?
That's 35.
36. 36 divided by negative 6?
That's 6.
That's definitely negative 6. What's 27 minus 9? 18. What's 18 divided by negative 6? Negative 3. So what have we just discovered? What x equals? How many things does x equal? 2 things. What does that mean? Guys, what does it mean? We have 2 solutions, right? Now look back. We have a parabola and a line, right? So it's going to be one of these things right here, right? And if I have 2 solutions, it's probably not going to look exactly like this, but the point I'm trying to make is there are 2 points of intersection here. My answer is not just negative 6, negative 3. My answer starts out like parenthesis negative 6, comma something, parenthesis negative 3, comma something, because all I found so far are the x values, right? How do I go about finding the y values? Is it exactly right? Okay. Would you choose to plug them into the top equation or the bottom equation?
The bottom one because it's smaller.
Bottom one because it's smaller. Okay. So y equals negative 3 times negative 6 minus 17. So when x is negative 6, what is negative 3 times negative 6? What's 18 minus 17? 1. So when x is negative 6, y is 1. Y equals negative 3 times negative 6 times negative 3 minus 17. What is negative 6 times negative? What did I do? This was a 3. I was right the first time. Sorry. What's negative 3 times negative 3? What is 9 minus 17? Negative 8. So when x equals negative 3, y equals negative 8. And in fact, that is our solution, isn't it? Okay? How do you feel about substitution? Okay. So let's do this problem next. God bless you. The directions for this problem say solve with elimination. Here's something I need you to understand about elimination. A lot of you, when we very first did systems of linear equations, we preferred elimination, right?
Over substitute.
Over substitution. A lot of you did. Now I know some of you like substitution better, and that's fine. But I'm telling you, elimination with non-linear systems, like this one with a quadratic and a line, it's not as easy. Because if I'm going to eliminate x's, which x's do I have to eliminate? I have to eliminate all of them, right? How can I eliminate when this one is squared and this one is not? How can I do that? Yeah, I can't, can I? Okay, so solving with elimination is going to be rare for us if we're trying to eliminate the x's. We can absolutely solve with elimination, no problem, if we are trying to eliminate the y's. Because in this particular problem, it's just a y and a y. If there was a y squared and a y, could I try elimination? No, not unless there was a y squared and a y squared and a y, and they were exactly the same but opposite. So that when I added them together, they went away, right? So most of the time, if there's an x squared and an x, we're not going to try to eliminate the x's. We're going to try to eliminate the y's instead. Does that make sense? Okay? I'm not saying we're going to never eliminate x's, because sometimes the y's might be squared. Okay? And then we would need to eliminate x's. But in this particular case, we're going to try to eliminate the y's. Okay? What has to be true for us to eliminate the y's? They have to be the same but opposite, right? So how could I make one of these opposite? I could just multiply one by a negative 1, right? One whole equation. So if I multiply this bottom equation by a negative 1, aren't I just changing the signs on every number? Okay? Let's just add them together exactly how they are. Are you okay with that? Now before, when we had systems of linear equations, I had to get them all in a correct order, right? Well, as long as these y's are together on one side of the equal sign, I'm fine. Okay? What's y and negative y? 0. What do I do with these two? Is that just like 2x? Or can I combine those at all? Yeah, I can't, right? They're different terms, or unlike terms. So I end up with negative 2x squared plus 4x. And what can I do with these two numbers? I sure can, right? I sure can combine those. Now, this is a quadratic that's equal to 0. We know how to solve those, don't we? Now, these were the options that I put forth for you before, and you automatically went to quadratic formula. But can I go back and say something real quick about this problem? If we're getting answers like negative 6 and negative 3, probably what I could have done from way up here is what? Factor it. I could have factored it, right? Because if I'm getting answers like negative 6 and negative 3, it could have been factored. Okay? Now, I didn't want to factor that the way it was because it looks messy and big numbers and lots of negatives, right? But do you notice all three of these numbers are divisible by 3? So if I would have divided by a 3 or a negative 3 to make my a term positive, do you think that might have made my problem easier from the very beginning so that I could see that it could be factored? Okay? So don't forget greatest common factor. Don't forget to eliminate. Why did I do quadratic formula here then? Because you said you wanted to sing. That's why we did quadratic formula, right? Sometimes I'm going to follow your lead. Sometimes I'm going to lead. Is that fair? Because I want to see how you're thinking so that I could guide you to different ways if necessary. We didn't do anything wrong, and we still got the right answer, didn't we? It might have been a little longer, but we know quadratic formula always works, don't we? Okay? So what could we do on this one from here to begin with? Before I try to do that, what should I maybe do? They are all divisible by what? I agree that they're all divisible by 2. What else are they all divisible by? How about a negative 2? Because if I divide out a negative 2, isn't my a term positive? And doesn't that usually make things easier for us? So then I get 0 equals x squared minus 2x plus 4. So regardless of the fact that if we try to factor or quadratic formula here, what I've already figured out is that this is already going to be easier because I've taken out a greatest common factor, right? It's a lot easier to see what I want to do, right? So what do you want to try to do here? Yeah, I would definitely try to factor it, right? Okay, so what multiplies to be 4 and adds to be negative 2? Uh-oh, right? So can we factor this one? No, but did we hurt anything by dividing by negative 2? No, it made it a little simpler for us, right? So if we're going to solve with the quadratic formula, I have to identify my variables, a, b, and c. X equals negative b plus or minus a square root b squared minus 4ac all over 2a. X equals 2 plus or minus the square root of 4 minus 16. What is 4 minus 16? Negative 12? I know I can break negative 12 up to be negative 1 times 4 times 3, right? And what's the square root of negative 1? I. What's the square root of 4? 2. What's the square root of 3? I don't know either. And what's true about all three of those numbers now? They're all divisible by 2, so we get, very good, 1 plus or minus I root 3. So what did we just discover? 1 plus 1 minus. How many x values do I have? I have 2, right? 1 plus I root 3 and 1 minus I root 3. But what else did I discover? It's a parabola and a line that have two, what kind of solutions? Imaginary. If there's two imaginary solutions, doesn't it look something like this graph?
Yes.
I'm not finding imaginary solutions. I'm only finding real solutions. So when I get here and realize that my solutions are imaginary, no real solutions. And I'm done. I don't have to go find the y values for imaginary solutions. I'm trying to find real solutions. Does that make sense?
Yes, ma'am.
Okay? Any questions about that? What is this? What shape is it? Do you know? They're both squared?
Oh, circle.
It is. They're both squared and they both have the same coefficient, so that's a circle. Okay? Now, I know the bell's about to ring. I'm going to finish this problem so that it's on the video that will be posted for you. This one just says solve. It doesn't say substitution or elimination. You have to just choose to solve it. But notice they're both squared, and there's no squareds in this bottom one, so can I do elimination? No? I want to do substitution. So I'm going to add x to both sides and get y equals x minus 1. I'm going to take the x minus 1 and I'm going to plug it in for y. So I get x squared plus x minus 1 squared equals 5. I need you to remember that x minus 1 squared is x minus 1 times x minus 1, and you have to distribute, otherwise you'll miss a middle term and you'll miss the problem. So x times x is x squared, x times negative 1 is negative 1x, negative 1 times x is negative 1x, and negative 1 times negative 1 is positive 1. So I get x squared. This right here is x squared minus 2x plus 1, and that equals 5. So now I want to combine my like terms, and I want to subtract my 5 all at the same time to get it equal to 0. So I have 2x squared minus 2x minus 4 equals 0. Everything is divisible by 2, so I'm going to divide everything by 2. And I'm going to get x squared minus x minus 2 equals 0. And finally, we have something we can factor. X minus 2, x minus 1. Because what multiplies to be negative 2 and adds to be negative 1, that's a negative 2 and a positive 1. Sorry, positive 1. Okay? I take each one of these factors and I set it equal to 0. So x equals 2 and x equals negative 1. So what I've just discovered is between my circle and my line, I have 2 points of intersection. One looks like 2 comma something, and one looks like negative 1 comma something. So to find the y value of each point, I'm going to go back up here. Y equals, first one I got was a 2, 2 minus 1. Well, 2 minus 1 is 1, so when x is 2, y is 1. And the second one, y equals negative 1 minus 1. Well, negative 1 minus 1 is negative 2. So when x equals negative 1, y equals negative 2. And those are my 2 solutions. Okay?